Yeah, good morning to all. We discussed last class about the hysteresis loss. So, in most cases, hysteresis is a levelity as it causes a dissipation of heat or waste of energy and harming due to the change in a polarity and rotation of electromagnet in the material. If a magnetic substance is magnetized in a strong magnetic field, it retains some portion of magnetism. After the magnetic force is withdrawn, the phenomenon of lagging of magnetization or induction flux density behind the magnetizing force is known as magnetic hysteresis. The loss due to the hysteresis are known as the hysteresis loss. Hysteresis loss depends upon the maximum flux density, that is, it is denoted a letter Bm, and the frequency of variation of flux is expressed as hysteresis loss is equal to eta into 1.6 into FBBm 1.6 joules per S, or watt. You can say it is a watt. So what is this? Eta is a constant. It is known as a Steinmann's hysteresis constant, or where the F is nothing but your frequency of reversal of magnetization. What is the Bm? The Bm is known as the maximum flux density, and this B is known as the volume of the magnetic material. So actually it is caused due to the polarity of rotation of an element magnet in the material. Due to the change in polarity or rotation of element magnet in the material, that is called as hysteresis. So we know all these things that. So we will discuss another loss is that is eddy current loss. You know guys about the eddy current loss. So when a magnetic material is placed in an alternating magnetic field, it cuts the magnetic flux. According to the law of electromagnetic induction, that is the Farad law of electromagnetic induction, an EMF is induced or induced EMF is produced. This EMF causes a current is known as the eddy current. The power loss due to the flow of this current is known as the eddy current loss. So this is the concept about the Farad law of electromagnetic induction. When you place a magnetic material is placed in an alternate magnetic field, it cuts the magnetic flux. According to the electromagnetic induction, an EMF is induced. This EMF causes current is known as the eddy current. This power loss due to the flow of current is known as the eddy current loss, and this eddy current loss is proportional to the square of the frequency and the same of the thickness of a material, and is inversely proportional to the resistivity of a material. That can be denoted as this expression. You can see P is equal to Ke. This is the constant. F square, this is the frequency, and this B max square, P square. So what is this? Another is B is also there. Okay. So what is this B? B is also there. So B is the volume of the material, T is the thickness of lamination, and K is the constant. This is called as eddy current loss. So what is the difference? Basic difference. You can see here. You can see the basic difference. What is the basic comparison of hysteresis loss and your versus your eddy current loss? So you can comparison by definition. Because the relative motion between the core and the magnetic force. Hysteresis loss when occur because the reversal of magnetism is known as hysteresis loss. This means when it is in north pole to south pole and it comes from south to north, this is a loss that is called the hysteresis loss. So at rotation of the loss is known as hysteresis loss, and the formula is it is Ke B F square T square B M B max square. But here in hysteresis it is K, or we can note it as eta B F B max 1.6 occurs. What is this occur? Interaction of magnetic flux and conductor. This occurs due to the interaction of magnetic flux and conductor. That's why it is it occurs due to the interaction between the magnetic flux and conductor. But hysteresis loss because of reversal of flux, that is known as minimizing method. What is the minimizing method? By making the core of a thin lamination, we can minimize the eddy current loss. Or hysteresis loss, by using a silicon steel material, we can reduce the hysteresis loss. This is the point to be noted, that hysteresis loss can be minimized by using a silicon steel material, or we can minimize the eddy current loss by making the core of a thin lamination. We have to be laminated, so that in this method we can minimize the loss of eddy current loss or hysteresis loss. So this is about your two types of loss, that is eddy current loss and hysteresis loss. Then we will go for Curie point. What is this point? This is called as a Curie point. So this is the one of the point, a critical temperature. So is the important things. You will get 2 marks in your semester examination. So Curie point, a critical temperature above which the ferromagnetic material loses their magnetic properties is known as a Curie point. It's the important thing. So a critical temperature above which the ferromagnetic material loses their magnetic properties. That means the ferromagnetic material loses their magnetic properties is known as a Curie point. So the hysteresis loop and the magnetic properties. We know that there is a one type of car. We can say this called as a BH hysteresis loop, or we already discussed about the magnetization curve, that is B and W versus H. So the hysteresis loop and the magnetic properties, a great deals of information can be learned about the magnetic properties of a material by studying this hysteresis loop. A hysteresis loop shows the relations between the induced magnetic flux density B and another one is magnetizing force H. It is often to refer as a BH loop, or it is often to as an example of hysteresis loop as shown in figure. You can see the figure here. So here is a B versus H car. You can see here axis is in H, y axis is in B. So this is the point from where the start A, B, C, D. Okay, then it goes to E, F, then it goes to again A. So it starts just like our magnetization from this here. So you know about all these things of the corrosivity and retentivity. Okay, these are the fundamental things. So we will discuss about the hysteresis loop and their magnetic properties. The loop is generated by measuring the magnetic flux B of a ferromagnetic material while magnetizing a force H. Change a ferromagnetic material that has never been previously magnetized or has been totally demagnetized will follow the dashed line of H as H is increased. So that means we can say we will discuss regarding this point as the line demonstrate the greater the amount of Curie, the amount of current is applied to H plus, the stronger the magnetic field in the component B plus. At point A, almost all of the magnetic domains are lignated, and additional increase in the magnetizing force will produce a very little increase in magnetic flux. The material has reached the point of a magnetic saturation. When H is reduced back down to 0, the car will move from the point A to B at this point. So you can see the diagram here. So you can see the diagram here, A to B. So you can see the diagram A to B here. You can see the diagram A to B here. It will the down back to the A to B. So here